Hey everybody, welcome to your introduction to our next unit, which is going to be all about solutions and solubility. And I wanted to start off today with a quick video just about solubility in hot versus cold water. So let's go ahead and take a look.
The right glass has hot water
So
and the left glass and the middle glass is cold water. Take a sugar cube and
our 2 cups
put
of
the
water,
sugar
one is
cube
cold and one is
each
hot, and placing a sugar cube in each. And
in
what
both the
you'll
glasses.
notice,
Then wait
and
and
what we
see
can
in which
record on
glass the
our
cube
note
dissolves
sheet
first.
is if
You will see that
can
there is
see
much more
how
activity in the
quickly
hot
the sugar
water
is
as compared
dissolving
to
in the
cold
hot
water.
water.
The sugar cube will dissolve more.
Something that I had that I wish that I had done, or there was no video for this, and I would totally recommend doing this at home. It's something that you guys can definitely do at home. Not just looking at how fast something dissolves in the water, right? That's what we're seeing here, how quickly the sugar cube is dissolving in the hot versus cold water. But what I'm really interested in is the amount of sugar that you can dissolve in hot versus cold water. And some of you, if you're experienced with sugar in your tea or coffee, this is something that you're gonna notice, or maybe you've already noticed in the past. If you go to, let's say, Dunkin' Donuts or Starbucks, you order an iced coffee and you want to add sugar to that coffee. If you try to add sugar to cold coffee, it really doesn't dissolve well. It ends up staying kind of granulated, versus if you add it to the hot coffee, it dissolves very easily into that hot coffee. The ability of the coffee to be hot, we'll talk about why it impacts it, but it can actually dissolve a lot more sugar as well. If you've ever made something like Jello at home, you will notice that in the instructions for Jello, it does specify that you do want to do this with hot water, boiling hot water, and that's so that you can get everything to dissolve into it. So, moral of the story, if you're interested, hot water dissolves a lot more sugar. I would recommend to give it a shot at home. Pour 1 cup of hot, 1 cup of cold, make them equal, obviously, use a measuring cup, and then see how many teaspoons of sugar you can add to hot versus cold water. All right, let's go ahead and jump into our notes sheet for today then. So I did want to just go ahead and record our observations from that. So the hot water dissolves the sugar, okay, faster. And again, I'm going to add in here, more sugar can dissolve. Okay, and then let's also add to that about the cold water here. So cold water dissolves sugar slower. And also just noting that if we were to test this, less sugar can dissolve. Okay, all right. And so what we're going to kind of focus on today is, why does hot water dissolve more than cold? Why does it dissolve faster? Why does it dissolve more sugar than, let's say, the cold water? Something that I want to just take a moment to review. It's been a while since we've talked about solutions. And I want to remind you guys that a solution, right, like sugar water, for example, is considered a homogeneous mixture. And we call it a homogeneous mixture because we can't see the difference. Once the sugar dissolves, it looks the same throughout. All of our particles have dispersed evenly through solution. Okay, so solutions are homogeneous, okay? And again, that means that they are dissolved completely and they look the same throughout. And that's going to be important because we are going to refer to solutions frequently, and understanding that the stuff that dissolves into the solution, right, the stuff that's actually dissolved is part of the solution. If you were, for instance, to have some of the solute that stays at the bottom, that's not actually part of the solution. That solute just sits at the bottom of the glass. It's undissolved. All right, so what is a solution created from? Okay, what is a solution created from? There are two main components to solutions. There's the solute and the solvent. And some of you guys may be familiar with these terms from middle school, but let's take a moment to review solute versus solvent. Okay, so a solute is the substance that is being dissolved. Okay, for the purpose of this course, we primarily focus on non-like phases being dissolved. So when we're talking about creating a solution, we're talking about usually taking a solute that is a gas or a solid and trying to dissolve that into a liquid. So for now, I'm going to put this as really gases or solids. Usually, they're the things that we are dissolving. Okay, for a solvent, and I've always hated this definition in this class, but just to kind of explain it, we describe it as the substance that does the dissolving. Okay, so this is our substance that does the dissolving. And so again, like I said, for the purpose of Regents level chemistry, we're going to focus on really gas and solid solutes being dissolved into liquid solvents. And this is going to be primarily water for the purpose of this course. I will say that you can make a solution from liquid solute and liquid solvent as well. But again, Regents level, we stick to usually gases and solids. So this creates a solution, okay? And so I want to go ahead and just quickly define solution again. I think we've already defined it once in this course, but we are always coming back and always tying new things in. So a solution is going to be a homogeneous mixture of two or more substances, right? And again, we've just defined those as the solute and solvent, okay? And I want to point out that again, I know I've just said this like 15 times, we primarily focus on water-based solutions. And so just as a refresher, AQ, the phase, represents an aqueous solution, okay? And that's one where water is the solvent, okay? And so, for example, if I were to write NaCl AQ, that means that NaCl is dissolved into water, okay? And we don't need to write plus water. The AQ already indicates that the water is part of our solution. And so in this case, we have NaCl, that's our solute. And we have our AQ, and that's our solvent. Okay, excellent. So we've talked about solubility before, right? This term solubility, and we looked at it in the video, why do things dissolve more in hot versus cold water? We have talked about the idea of solubility in this class before in two different ways. The first, just as a refresher, is going to be from reference table F. Solubility Guidelines. So what I want you to actually do is pause this video, take a moment, see if you can find something that is considered soluble versus something that is considered insoluble on your reference table. So go ahead, take a moment, pause this, fill this in to the best of your ability, and then we'll come back and go over it. So welcome back. Hopefully you've paused. If you did not pause, that's okay. Reference table F again is solubility guidelines. So something that is considered soluble. Okay, I like to use NH4, NO3. This is ammonium nitrate. I selected this one, and again, obviously you might not have selected the same one. I picked this one because ammonium NH4 is always soluble. There are no exceptions. And nitrates are always soluble. There are no exceptions. So when they're paired together, it's going to be soluble. Okay, something that is considered insoluble, okay, would be something like AgCl, okay, silver chloride. Again, halides like fluorine, chlorine, bromine, okay? They're going to be always soluble, but there are some exceptions to that rule, and they become insoluble, meaning they won't dissolve when there is lead, silver, or mercury, okay? And so we end up with silver chloride being an insoluble compound, okay? Now, we've also talked about solubility in terms of polarity. So I want you to take a moment, pause the video, and think to yourself, what is the rule about polarity and solubility? All right, so welcome back. If you didn't pause and you're just following along, that's okay. Remember that in our solubility units, or I'm sorry, when we were talking about molecular polarity, we talked about mixtures being able to come together when they had the phrase like dissolves like, okay? Meaning, and I'm gonna actually just write that here, like dissolves like. Okay, and again, the idea is that things will be soluble together if they have the same molecular polarity. So same molecular polarity means two substances will dissolve. Okay, so we've looked at basically at this point solubility as being black and white, if you will, okay? That something is either soluble or it's insoluble, and that's it. There is no range of solubility. But what we're going to talk about in this unit specifically is that solubility actually is not black and white, okay? Solubility is a range. There are certain things that dissolve more than others or less than others, even though they both theoretically dissolve. And so what I want to do is redefine solubility for this unit, and we're going to define solubility as being the extent to which a solute is able to dissolve, okay? So they might both be able to dissolve, but one of them might be more soluble than the other. And so it's the extent to which a solute is able to dissolve in a solvent. Okay, so what makes something more or less soluble? How can we improve solubility? How can we get something to dissolve more? Well, interestingly, we're going to talk about, again, I said solutes are really going to be defined as either gases or solids. And so we're going to talk about the ways to increase both the gas solubility or solid solubility. Now, in our video from the beginning of this lesson, we watched, sugar being dissolved. So sugar, again, is a solid solute. So how can we get sugar to dissolve more? And that's going to be with an increase in temperature, right? So we're going to increase temperature in order to get solids to dissolve more. And if you think about it, why would that be the case? Well, we have our particles moving faster, which allows the particles to kind of pull apart the other particles quicker, okay? Now let's talk about gases, okay? And so in order to introduce gas solubility, you might be thinking, I've never really thought of a gas being dissolved into a liquid before. And you may or may not think of it, but actually soda, I love Diet Pepsi, which is why I've included that, but seltzer, soda, whatever soda you like, that's actually gas dissolved into a liquid. And so in order to talk about how to get something or gases to get dissolved into a liquid more, I wanted to use soda. So why is soda considered a solution? And actually, if you want to take a moment and pause and think about all of these questions, I urge you to do that. But if you want to follow along, that's okay too. So why is soda considered a solution? It's a solution because we have both sugar and CO2 dissolved in H2O, right? We have two solutes here, really. We have our sugar solute, or sugar substitute if you're talking about a diet soda, and we have our CO2 as our solute, and our solvent is water-based. okay? Now, in terms of intermolecular forces, why will soda go flat when it's left open? So think about a can of soda. You crack it open, you hear the most satisfying, delicious sounding, like fizzing of bubbles. But that fizzing of bubbles means that the gas is coming out of the water or coming out of your soda. So if I leave my can of soda open for long enough, why is that the case? Well, in order to answer that, we need to go back to that idea of molecular polarity. Our solvent, water, is polar, okay? And our solute of carbon dioxide is nonpolar. So the gas, the CO2, really doesn't want to stay dissolved into water, right? So the CO2 is nonpolar, which makes it harder to dissolve. I don't know why there we go, to dissolve in water, which is polar, okay? And so there are ways that we can help increase the solubility of that CO2. So I always tell my students to think of the perfect can of soda. And again, this varies for everybody, but what conditions would you drink that soda in? And let's first start with temperature. Remember, for the solids, we said increasing temperature helps with the solubility, with the sugar to dissolve in. But would increasing temperature help CO2 dissolve? The answer is no, okay? If you heat up a gas, what happens? Our particles start to move faster and they start to spread out. And so we really want the coolest temperature possible. So we want to have low temperature, okay, for soda. And again, if you think about it, drinking a can of soda, you don't want to drink hot soda anyways. You want it to be nice and cold. And so I want to go back up and fill that into our little chart here. How can we increase gas solubility? We want lower temperatures, okay? And then lastly, what else can we do to help increase the solubility of a gas? Well, when you go to buy a can of soda, or if you were to get a can of soda or a bottle of soda, and you were to squeeze that soda, you should feel it pressurized, right? So when we put or apply pressure, think about it from our last unit, our gas laws unit. Applying pressure, right? Increased pressure means decreased volume. We're forcing that gas into a smaller amount of space. Essentially, we're creating all of this carbonation in our soda by forcing the CO2 into the smaller amount of space. So when you get a can of soda, you really want it to have high pressure, okay? And that's going to help us with keeping our CO2 dissolved, high pressure. And again, let's just go back up quickly and add that into our thing. Now, will pressure have an effect on solid solubility? And I want you to think about that for class tomorrow. Will pressure impact solid solubility? Why or why not? All right, everybody, thank you. I will see you guys tomorrow.